friends, in the previous session we learned inner product spaces. Now we discuss the perpendicularity of some vectors in an inner product space. In this session we will define orthogonal and orthonormal vectors. We will see that from a linear independent set of vectors, it is possible to obtain a set of orthogonal vectors such that span of the linearly independent set and the span of the orthogonal set are the same. We also describe best approximation of a vector from vectors in a subspace, orthogonal complement of a set and orthogonal projection of a vector to a subspace. We conclude the session by describing Bessel's inequality. Orthogonal set. Definition. Let alpha and beta be vectors in an inner product space V. Then alpha is orthogonal to beta if inner product alpha beta is equal to 0. We simply say that alpha and beta are orthogonal. If S is a set of vectors in V, S is called an orthogonal set provided all pairs of distinct vectors in S are orthogonal. An orthonormal set is an orthogonal set S with the additional property that norm of alpha is equal to 1 for every alpha in S. Example 1. The 0 vector 0 is orthogonal to every vector in V and is the only vector with this property. Example 2. The standard basis set E1 is equal to 1 0 0 etc 0 etc. En is equal to 0 0 0 etc 1 of Kn, where Kn is either Rn or Cn, is an orthonormal set with respect to the standard inner product. The verification is very simple and is left as an exercise to the student. Example 3. The vector xy in R2 is orthogonal to minus yx in R2 with respect to the standard inner product because inner product xy minus yx is equal to minus xy plus yx, which is equal to 0. However, if R2 is equipped with the inner product defined for x is equal to x1 x2 and y is equal to y1 y2 in R2 by inner product alpha beta is equal to x1 y1 minus x2 y1 minus x1 y2 plus 4x2 y2. Then xy and minus yx are orthogonal if and only if y is equal to 1 by 2 into minus 3 plus or minus root of 13x. Theorem 1. An orthogonal set of non-zero vectors is linearly independent. Proof. Let S be a finite or infinite set of non-zero vectors in a given inner product space. Suppose alpha 1, alpha 2 etc. alpha n are distinct vectors in S and that beta is equal to C1 alpha 1 plus C2 alpha 2 plus etc. plus Cn alpha n. Then inner product beta alpha k is equal to inner product C1 alpha 1 plus C2 alpha 2 plus etc. plus Cn alpha n alpha k, which is equal to C1 inner product alpha 1 alpha k plus C2 inner product alpha 2 alpha k plus etc. plus Cn inner product alpha n alpha k, which is equal to Ck inner product alpha k. Since inner product alpha j alpha k is equal to 0 if I not equal to j equal to 1 if I equal to j. Also alpha k being non-zero, inner product alpha k not equal to 0 and hence division by inner product alpha k is possible, and from the above it follows that Ck is equal to inner product beta alpha k by inner product alpha k or Ck is equal to inner product beta alpha k by norm alpha k square 1 less than or equal to k less than or equal to m. Thus, when beta is equal to 0, each Ck is equal to 0. So, S is a linearly independent set. Corollary 1. If a vector beta is a linear combination of an orthogonal sequence of non-zero vectors alpha 1, alpha 2 etc. alpha m, then beta is the particular linear combination. Beta is equal to sigma k is equal to 1 to m inner product beta alpha k by norm alpha k square alpha k. Equation number 1. Proof. Since beta is a linear combination of an orthogonal sequence of non-zero vectors alpha 1, alpha 2 etc. alpha n, we can write beta is equal to C1 alpha 1 plus C2 alpha 2 plus etc. plus Cn alpha n, where Ck is equal to inner product beta alpha k by norm alpha k square 1 less than or equal to k less than or equal to m. Hence, beta is equal to sigma k is equal to 1 to n inner product beta alpha k by norm alpha k square. Corollary 2. If set alpha 1, alpha 2, etc. alpha n is an orthogonal set of non-zero vectors in a finite dimensional inner product space V, then M less than or equal to dimension V. That is, the number of mutually orthogonal vectors in V cannot exceed the dimension of V. Gram-Schmidt orthogonalization process. The following theorem provides a method known as the Gram-Schmidt orthogonalization process for obtaining an orthogonal set from a linearly independent set such that span of both sets are the same. Theorem 2. Gram-Schmidt orthogonalization process. Let V be an inner product space and set beta 1, beta 2, etc. beta m be any linearly independent vectors in V. Then one may construct orthogonal vectors alpha 1, alpha 2, etc. alpha n in V such that for each k is equal to 1, 2, etc. n, the set alpha 1, alpha 2, etc. alpha k is an orthogonal basis for the subspace of V spanned by beta 1, beta 2, etc. beta k. Proof. The vectors alpha 1, alpha 2, etc. alpha n are obtained by means of the following construction. First, let alpha 1 is equal to beta 1. The other vectors are then given inductively as follows. Suppose alpha 1, alpha 2, etc. alpha m 1 less than or equal to m less than n have been chosen so that for every k, set alpha 1, alpha 2, etc. alpha k 1 less than or equal to k less than or equal to m is an orthogonal basis for the subspace of V that is spanned by beta 1, beta 2, etc. beta k. To construct the next vector, let alpha m plus 1 is equal to beta m plus 1 minus sigma k is equal to 1 to m inner product beta m plus 1 alpha k by norm alpha k square alpha k. Then alpha m plus 1 not equal to 0, for otherwise beta m plus 1 minus sigma k is equal to 1 to m inner product beta m plus 1 alpha k by norm alpha k square alpha k is equal to 0 implies beta m plus 1 is equal to sigma k is equal to 1 to m inner product beta m plus 1 alpha k by norm alpha k square alpha k implies beta m plus 1 is a linear combination of alpha 1, alpha 2, etc. alpha m, and hence a linear combination by the induction argument of beta 1, beta 2, etc. beta m, a contradiction. Also, if 1 less than or equal to j less than or equal to m, then inner product alpha m plus 1 alpha j is equal to inner product beta m plus 1 alpha j minus sigma k is equal to 1 to m inner product beta m plus 1 alpha k by norm alpha k square inner product alpha k alpha j, which is equal to inner product beta m plus 1 alpha j minus inner product beta m plus 1 alpha j using the orthonormality of alpha 1, alpha 2, etc. alpha m, which is equal to 0. Therefore, set alpha 1, alpha 2, etc. alpha m plus 1 is an orthogonal set consisting of m plus 1 non-zero vectors in the subspace spanned by beta 1, beta 2, etc. beta m plus 1. Hence, by an earlier theorem, it is a basis for this subspace. Thus, the vectors alpha 1, alpha 2, etc. alpha n may be constructed using the formula alpha m plus 1 is equal to beta m plus 1 minus sigma k is equal to 1 to m in a product beta m plus 1 alpha k by norm alpha k square alpha k. In particular, when n is equal to 3, we have alpha 1 is equal to beta 1, alpha 2 is equal to beta 2 minus inner product beta 2 alpha 1 by norm alpha 1 square alpha 1, alpha 3 is equal to beta 3 minus inner product beta 3 alpha 1 by norm alpha 1 square into alpha 1 minus inner product beta 3 alpha 2 by norm alpha 2 square into alpha 2. This completes the proof. Definition. A set of vectors in a vector space is an orthonormal basis of it if the set is an orthonormal set that is also a basis for the vector space. Corollary 3. Every finite dimensional inner product space has an orthonormal basis. Proof. Let V be an finite dimensional inner product space and set beta 1, beta 2, etc. beta n a basis for V. Apply the Gram-Schmidt orthonormalization process to construct an orthogonal basis set alpha 1, alpha 2, etc. alpha n. Then, to obtain an orthonormal basis, simply replace each vector alpha k by norm alpha k, so that the new collection set alpha 1, alpha 2, etc. alpha n is an orthonormal basis. Example 4. In R3, equipped with the standard inner product, consider the linearly independent vectors beta 1 is equal to 1, 1, 1, beta 2 is equal to 1, 0, 1, beta 3 is equal to 1, 1, 0. From this, obtain the orthogonal basis of R3. Solution. Applying the Gram-Schmidt or process to beta 1, beta 2, beta 3, we obtain the following. Vectors orthogonal to each other. Alpha 1 is equal to 1, 1, 1. Alpha 2 is equal to 1, 0, 1 minus inner product 1, 0, 1, 1, 1, 1 by norm 1, 1, 1 square 1, 1, 1, which is equal to 1, 0, 1 minus 1 plus 0 plus 1 by square root of 1 square plus 1 square plus 1 square whole square into 1, 1, 1, which is equal to 1, 0, 1 minus 2 by 3 times 1, 1, 1, which is equal to 1 by 3 minus 2 by 3, 1 by 3. Alpha 3 is equal to 1, 1, 0 minus inner product 1, 1, 0, 1, 1, 1 by norm 1, 1, 1 square into 1, 1, 1 minus inner product 1, 1, 0, 1 by 3 minus 2 by 3, 1 by 3 by norm 1 by 3 minus 2 by 3, 1 by 3 square into 1 by 3 minus 2 by 3, 1 by 3, which is equal to 1, 1, 0 minus 2 by 3 into 1, 1, 1 plus 1 by 2 into 1 by 3 to minus 2 by 3, 1 by 3, which is equal to 1 by 2, 0 minus 1 by 2. Since the vectors are non-zero and mutually orthogonal, verification is left to the assignments. We have set alpha 1, alpha 2, alpha 3 is an orthogonal basis for R3. To express an arbitrary vector x1, x2, x3 in R3 as a linear combination of alpha 1, alpha 2, alpha 3, it is not necessary to solve any linear equations. For it suffices to use the relation 1 in corollary 1 to theorem 1 above. Thus, x1, x2, x3 is equal to sigma k is equal to 1 to 3 in a product x1, x2, x3 alpha k by norm alpha k square into alpha k, which is equal to in a product x1, x2, x3 1, 1, 1 by norm 1, 1, 1 square into alpha 1 plus in a product x1, x2, x3 1 by 3 minus 2 by 3, 1 by 3 by norm 1 by 3 minus 2 by 3, 1 by 3 square alpha 2 plus in a product x1, x2, x3 1 by 2 0 minus 1 by 2 by norm 1 by 2 0 minus 1 by 2 square alpha 3. That is x1, x2, x3 is equal to x1 plus x2 plus x3 by 3 alpha 1 plus x1 minus 2x2 plus x3 by 2 alpha 2 plus x1 minus x3 alpha 3. In particular, 1, 2, 3 is equal to 2 alpha 1 plus 0 alpha 2 minus 2 alpha 3, which is equal to 2 into 1, 1, 1 plus 0 into 1 by 3 minus 2 by 3, 1 by 3 minus 2 into 1 by 2, 0 minus 1 by 2. To put this point in another way, what we have shown is the following. The basis set f1, f2, f3 of R3 star, which is dual to the basis alpha 1, alpha 2, alpha 3 is defined explicitly by the equations f1 of x1, x2, x3 is equal to 3x1 plus 4x2 by 25. f2 of x1, x2, x3 is equal to minus 4x1 plus 3x3 by 25. f3 of x1, x2, x3 is equal to x2 by 9. And these equations may be written more generally in the form fj of x1, x2, x3 is equal to x1, x2, x3 by alpha j by norm alpha j square. Finally, note that from alpha 1, alpha 2, alpha 3, we get the orthonormal basis 1 by 5, 3, 0, 4, 1 by 5, minus 4, 0, 3, 0, 1, 0. Best approximation. Definition. A best approximation to beta in V by vectors in a subspace W of V is a vector alpha in W such that norm of beta minus alpha less than or equal to norm of beta minus gamma for every vector gamma in W. Theorem 3. Let W be a subspace of an inner product space V and let beta belongs to V. The vector alpha belongs to W is a best approximation to beta belongs to V by vectors in W if and only if beta minus alpha is orthogonal to every vector in W. If a best approximation to beta in V by vectors in W exists, it is unique. If W is finite dimensional and set alpha 1, alpha 2, etc. alpha n is any orthonormal basis for W, then the vector alpha is equal to sigma k is equal to 1 to n inner product beta alpha k by norm alpha k square alpha k is the unique best approximation to beta by vectors in W. Proof. First note that if gamma is any vector in V, then beta minus gamma is equal to beta minus alpha plus alpha minus gamma, and norm of beta minus gamma square is equal to norm of beta minus alpha square plus 2 times real part of inner product beta minus alpha, alpha minus gamma plus norm of alpha minus gamma square. Now suppose beta minus alpha is orthogonal to every vector in W, that is gamma in W, and that gamma naught is equal to alpha. Then since alpha minus gamma belong to W, it follows that norm of beta minus gamma square is equal to norm of beta minus alpha square plus norm of alpha minus gamma square, which is greater than norm of beta minus alpha square. Conversely, suppose that norm of beta minus gamma greater than or equal to norm of beta minus alpha for every gamma in W. Then from the equation above, it follows that 2 times real part of inner product beta minus alpha, alpha minus gamma plus norm of alpha minus gamma square greater than or equal to 0 for every gamma in W. Since every vector in W may be expressed in the form alpha minus gamma with gamma in W, we see that 2 real part of inner product beta minus alpha tau plus norm tau square greater than or equal to 0 for every tau in W. In particular, if gamma belongs to W and gamma not equal to alpha, we may take tau is equal to minus inner product beta minus alpha, alpha minus gamma by norm alpha minus gamma square into alpha minus gamma. Then the inequality reduces to the statement minus 2 modulus of inner product beta minus alpha, alpha minus gamma square by norm alpha minus gamma square plus modulus of inner product beta minus alpha, alpha minus gamma square by norm alpha minus gamma square greater than or equal to 0. That is to the statement modulus of inner product beta minus alpha, alpha minus gamma square by norm alpha minus gamma square less than or equal to 0. This holds if and only if inner product beta minus alpha, alpha minus gamma is equal to 0, since modulus and norm functions are always non-negative. Therefore, beta minus alpha is orthogonal to every vector in W. This completes the proof of the equivalence of the two conditions on alpha given in 1. The orthogonality condition is evidently satisfied by at most one vector in W, which proves 2. Now suppose that W is a finite dimensional subspace of V. Then we know as a corollary of theorem that W has an orthogonal basis. Let alpha 1, alpha 2, etc. alpha n be any orthogonal basis for W and define alpha by alpha is equal to sigma k is equal to 1 to n inner product beta alpha k by norm alpha k square into alpha k. Then by the computation in the proof of theorem, beta minus alpha is orthogonal to each of the vectors alpha k. Beta minus alpha is the vector obtained at the last stage when the orthogonalization process is applied to alpha 1, alpha 2, etc. alpha n beta. Thus, beta minus alpha is orthogonal to every linear combination of alpha 1, alpha 2, etc. alpha n, that is to every vector in W. If gamma belongs to W and that gamma not equal to A, it follows that norm of beta minus gamma greater than norm of beta minus alpha. Therefore, alpha is equal to sigma k is equal to 1 to n inner product beta alpha k by norm alpha k square alpha k is the unique best approximation to beta by vectors in W. Orthogonal complement of a set. Definition. Let V be an inner product space and S any set of vectors in V. The orthogonal complement of S is the set S perp of all vectors in V which are orthogonal to every vector in S. That is, S perp is equal to set of all alpha in V such that inner product beta alpha is equal to 0 for every beta in S. S perp is read as perp. Example 5. The orthogonal complement of V is set 0. That is, V perp is equal to set 0. Conversely, set 0 perp is equal to V. Theorem 4. If S any subset need not be subspace of V, then its orthogonal complement S perp is always a subspace of V. Proof. S perp is non-empty because 0 belongs to S perp. Also, whenever alpha beta belongs to S perp and C in F, then gamma belongs to S, we have inner product C alpha plus beta gamma is equal to C into inner product alpha gamma plus beta gamma, which is equal to C into 0 plus 0, showing that C alpha plus beta belong to S perp and hence S perp is a subspace of V. Orthogonal projection. Definition. Whenever the vector alpha in theorem 3 exists, it is called the orthogonal projection of beta on W. If every vector in V has an orthogonal projection on W, the mapping that assigns to each vector in V its orthogonal projection on W is called the orthogonal projection of V on W. Corollary 4. Let V be an inner product space, W a finite dimensional subspace, and E the orthogonal projection of V on W. Then the mapping beta from beta minus E beta is the orthogonal projection of V on W perp. Proof. Let beta belongs to V, then beta minus E beta belongs to W perp, and for any gamma in W perp, beta minus gamma is equal to E beta plus beta minus E beta minus gamma. Since E beta belongs to W and beta minus E beta minus gamma belongs to W perp, it follows that norm of beta minus gamma square is equal to inner product E beta plus beta minus E beta minus gamma E beta plus beta minus E beta minus gamma, which is equal to norm of E beta square plus norm of beta minus E beta minus gamma square, which is greater than or equal to norm beta minus E beta whole square, with strict inequality when gamma not equal to beta minus E beta. Therefore, beta minus E beta is the best approximation to beta by vectors in W perp. Example 6. Consider R2 with the standard inner product. Then the orthogonal projection of beta is equal to 2, 1 on the subspace W that is spanned by 0, 1 is the vector alpha is equal to inner product 2, 1, 1, 0 by norm 1, 0 square into 1, 0, which is equal to 2, 0. The orthogonal projection of beta is equal to 2, 1 on the subspace U that is spanned by 0, 1 is the vector alpha is equal to inner product 2, 1, 0, 1 by norm of 0, 1 square into 0, 1 is equal to 0, 1. In the above, we note that W is the x-axis and U is the y-axis. The orthogonal projection beta is equal to 2, 1 on the subspace V that is spanned by 1, 1 is the vector alpha is equal to inner product 2, 1, 1, 1 by norm 1, 1 square into 1, 1, which is equal to 3 by 2, 3 by 2. Example 7. Consider R3 with the standard inner product. Then the orthogonal projection beta is equal to minus 10, 2, 8 of the subspace W that is spanned by 3, 12, minus 1 is the vector alpha is equal to inner product minus 10, 2, 8, 3, 12 minus 1 by 9 plus 144 plus 1 into 3, 12 minus 1, which is equal to minus 14 by 154 into 3, 12 minus 1. The orthogonal projection of R3 on W is the linear transformation E defined by x1, x2, x3 to 3x1 plus 12x2 minus x3 by 154 into 3, 12 minus 1. The rank of E is clearly 1, hence its nullity is 2. On the other hand, E of x1, x2, x3 is equal to 0, 0, 0. If and only if 3x1 plus 12x2 minus x3 is equal to 0. This is the case if and only if x1, x2, x3 belongs to W perp. Therefore, W perp is the null space of E and dimension of W perp is equal to 2. Computing x1, x2, x3 minus 3x1 plus 12x2 minus x3 by 154 into 312 minus 1, we say that the orthogonal projection of R3 on W perp is the linear transformation I minus E that maps the vector x1, x2, x3 onto the vector 1 by 154 into 145x1 minus 36x2 plus 3x3 minus 36x1 plus 10x2 plus 12x3, 3x1 plus 12x2 plus 153x3. The following result generalizes the idea in the example. Theorem 5. Let W be a finite dimensional subspace of an inner product space V and let E be the orthogonal projection of V on W. Then E is an idempotent linear transformation of V onto W. W perp is the null space of E and V is equal to W direct sum W perp. Proof. Let beta be an arbitrary vector in V. Then E beta is the best approximation to beta that lies in W. In particular, E beta is equal to beta when beta is in W. Therefore, E of E beta is equal to E beta for every beta in V. That is, E is idempotent. E square is equal to E. To prove that E is linear transformation, let alpha and beta be any vectors in V and C an arbitrary scalar. Then by theorem 4, alpha minus E alpha and beta minus E beta are each orthogonal to every vector in W. Hence the vector C into alpha minus E alpha plus beta minus E beta is equal to C alpha plus beta minus C E alpha plus E beta also belongs to W perp. Since C E alpha plus E beta is a vector in W, it follows from theorem that E of C alpha plus beta is equal to C E alpha plus E beta. Again, let beta be any vector in V. Then E beta is the unique vector in W such that beta minus E beta is in W perp. Thus, E beta is equal to 0 when beta is in W perp. Conversely, beta is in W perp when E beta is equal to 0. Thus, W perp is the null space of E. The equation beta is equal to E beta plus beta minus E beta shows that V is equal to W plus W perp. Moreover, W intersection W perp is equal to set 0. For if alpha is a vector in W intersection W perp, then alpha by alpha is equal to 0. Therefore, alpha is equal to 0 and V is the direct sum of W and W perp. Corollary 5. Under the conditions of the theorem, I minus E is the orthogonal projection of V on W perp. It is an idempotent linear transformation of V onto W perp with a null space W. Proof. We have already seen that the mapping beta from beta minus E beta is the orthogonal projection of V on W perp. Since E is a linear transformation W perp, this projection on W perp is the linear transformation I minus E. From its geometric properties, one sees that I minus E is an idempotent transformation of V onto W. This also follows from the computation. I minus E into I minus E is equal to I minus E minus E square, which is equal to I minus E. Moreover, I minus E into beta is equal to 0 if and only if beta is equal to E beta, and this is the case if and only if beta is in W. Therefore, W is the null space of I minus E. The Gram-Schmidt process may now be described geometrically in the following way. Given an inner product space V and vectors beta 1 etc. beta n in V, let Pk where k greater than 1 be the orthogonal projection of V on the orthogonal complement of the subspace spanned by beta 1 etc. beta k minus 1 and the set P1 is equal to 1. Then the vectors 1 obtained by applying the orthogonalization process to beta 1 etc. beta n are defined by the equations alpha k is equal to Pk beta k, 1 less than or equal to k less than or equal to n. Bessel's inequality. The following is a consequence of theorem 5. Corollary 6. Bessel's inequality. Let set alpha 1 etc. alpha n be an orthogonal set on non-zero vectors in an inner product space V. If beta is any vector in V, then sigma over k mod beta by alpha k square by norm alpha k square less than or equal to norm beta square, and equality holds if and only if beta is equal to sigma over k beta by alpha k square by norm alpha k square alpha k. Proof. Let gamma is equal to sigma over k beta by alpha k by norm alpha k square alpha k. Then beta is equal to gamma plus delta, where gamma by delta is equal to 0. Hence, norm of beta square is equal to norm of gamma square plus norm of delta square. It now suffices to prove that norm of gamma square is equal to sigma over k modulus of beta by alpha k square by norm alpha k square. This is straightforward computation in which one uses the fact that alpha j by alpha k is equal to 0 for j not equal to k. In the special case in which set alpha 1 etc. alpha n is an orthogonal set, Bessel's inequality says that sigma over k norm beta by alpha k square less than or equal to norm beta square. The corollary also tells us in this case that beta is in the subspace spanned by alpha 1 etc. alpha n if and only if beta is equal to sigma over k beta by alpha k into alpha k, or if and only if Bessel's inequality is actually an equality. Of course, in the event that V is finite dimensional and set alpha 1 etc. alpha n is an orthogonal basis for V, the above formula holds for every vector beta in V. In other words, if set alpha 1 etc. alpha n is an orthonormal basis for V, the kth coordinate of beta in the ordered basis alpha 1 etc. alpha n is beta by alpha k. Now, it is time to summarize the session. In this session, we discussed properties of inner product spaces, especially orthogonal sets. Gram-Schwarz orthogonalization process with examples and Bessel's inequality are introduced, which are fundamental in the study of inner product spaces. Before going to the next session, let us try to answer these questions. Consider the vector space V is equal to P3 of minus 1, 1 of all real polynomial function P of x, x in minus 1, 1 of degree at most 3. Let the inner product on V be given by for PQ in V, inner product PQ is equal to integral minus 1 to 1 P of t Qt dt. Find the orthonormal basis that can be obtained from the basis set 1 x, x square, x cube. Let V be an inner product space and W be a subspace of it. Let E be an orthogonal projection of V onto W. Show that I minus E is an orthogonal projection onto W perp. Let set alpha 1 etc. alpha n be an orthonormal set in an inner product space V. Show that if beta is any vector in V, then sigma over k modulus of beta alpha k square less than or equal to norm beta square. Consider R4 with standard inner product. Let W be the subspace of R4 consisting of all vectors which are orthogonal to both alpha is equal to 1, 0, minus 1, 1 and beta is equal to 2, 3, minus 1, 2. Find a basis for W. Hope you enjoyed this session. See you next time. Till then, goodbye.